Hello. So today we are going to discuss the adder circuit. Now the adder circuit in digital electronics is a combinational circuit. So first we need to go through what does this term combinational mean? What is a combinational circuit? So a combinational circuit is essentially where the output at time t consists of only the present inputs. It only considers the present inputs. This thing needs to be remembered. This is what makes up a combinational circuit. The output at any time instance t is dependent only on the present input. It does not depend on any previous input. No previous input is considered. So this is what makes up a combinational circuit, and any combinational circuit can have n number of inputs and m number of outputs. Where the purpose of the circuit is known, we should be able to first identify what are the number of inputs in this circuit and what are the number of outputs in this circuit. Now the circuit that we have currently considered is called adder, right? And it is supposed to perform binary addition. An adder circuit is supposed to perform binary addition. There are two types of adder circuits that we need to consider. The first one is called half adder, and the other one is called the full adder. And these two have a subtle difference which we will come to in due time. So today we will first discuss the circuit called half adder. Now whenever we are starting off discussing any circuit, we need to understand its basic characteristics. The half adder circuit can add two 1-bit inputs, right? And it can produce two outputs. What are the outputs called? For addition, there are two possible outputs. One is called sum and the other one is called carry. For example, if you are adding two 1-bit inputs, both are 1. So what is the result? It results in 1 0. What is this 0 bit called? This 0 bit is called the sum, and this 1 is called the carry bit. So this is your results of the half adder circuit. So imagine that there is a black box, a box whose inner contents are not known to you, and this is your half adder. So we can say that on providing two inputs to this half adder circuit, one input being A and the other input being B, this half adder circuit produces two outputs. One is called sum and the other is called carry. Whenever you are working with any circuit in digital electronics, the first step is to build this block diagram. This is called the block diagram. So what does the block diagram represent? It represents the overall functioning of the circuit. So given any two 2-bit inputs, it results in two outputs, one of which is called the sum and the another one is called the carry. Fine. So this is the first step towards addressing this half adder circuit. After taking a look at this block diagram, next we need to understand what actually happens in the half adder circuit. For that we need to have a knowledge of binary arithmetic, because this is an adder circuit. So binary addition we need to know. If we know binary addition, then we will be able to build something called the truth table. What happens in a truth table? In a truth table, you write down the sets of inputs and the sets of outputs. You write down the sets of inputs and the sets of outputs very clearly. You need to mention for what input, what value of output you are going to get. So consider that there are two bits here, A and B. So how many possible input combinations are possible? Each of A and B, each one can take either 0 or 1, right? So there are 2 square possible combinations. That means there are 4 possible combinations of binary inputs possible for the half adder. What are these combinations? They are 0 0, 0 1, 1 0 and 1 1. Or decimal equivalents are 0, 1, 2 and 3, right? So these are the 4 possible combinations that can be given as input in the half adder circuit. And as a result of these inputs, what is the sum and what is the carry bit that is generated? So whenever we are adding 0 and 0, what is the sum? 0. Carry is also 0. When we are adding 0 and 1, the sum is 1, the carry is 0. Similarly, 1 added to 0 is 1 in the sum, carry is 0. Finally, when we add 1 plus 1, we get a sum of 0 and carry as 1. So this is what we get in the form of a truth table. So what have we seen so far? We have seen that for the half adder circuit, there has to be 2 inputs and 2 outputs. And we know specifically for what input combination, what is the set of outputs that we are going to get, right? And this knowledge will help us better define the half adder circuit's internal circuitry in terms of the basic gates that we have learned. So the next step is to determine the different K-maps. Now why do we use K-maps? K-maps always result in giving us the minimal logic expression. They result in giving us the minimal logic expression or the shortest logic expression that is possible to build that circuit. So for doing this job, we need to identify what is the K-map for sum and carry separately, right? So first let us consider sum. So for sum, we have 2 inputs A and B and we have 1 output S. The input combinations were 0, 0, 0, 1, 1, 0 and 1, 1. Here, what is the output sequence of sum? 0, 1, 1, 0. This is the output sequence for sum. So if we want to design the K-map for sum, what will it be? It will be a very simple K-map. On one side of the K-map, we will have the input A. On the other side, we will have the input B. And on both sides, we will have only 0, 1, 0, 1. So in which particular situations do we have output 1? For A0, B1, I have sum as 1. Also, for A1, B0, I have the sum as 1. And we already know that in a K-map, we cannot actually make diagonal pairs. It is not possible to make diagonal pairs. So these values have to be considered individually in order to identify the sum of product form. Here no grouping is possible, right? So for this particular one, what is the S.O.P term? What should be the term? We have A as 1 here, so A will be as it is, and we have B 0, so we will have to take B complement. So it becomes A and B complement. Similarly, for this one, how do we get the term? We get A as 0, so we have to take A complement and B is already 1, so A complement and B, right? So our sum comes out to be S equal to A complement B or AB complement. And from the knowledge of the basic gates, we already know that this is representative of the XOR gate, XOR gate or XOR gate. So A XOR B, that is the expression that we get for sum. Next, we will repeat the same set of steps for carry, for the carry bit. So we will write K-map for carry. In case of the carry bit again, we will write down the 2 inputs A and B and the output is carry out. We have the inputs as 0, 0, 0, 1, 1, 0 and 1, 1. And for the carry bit, for 2 inputs 0, 0, carry is 0, 0 and 1, carry is 0, 1, 0, carry is again 0. Only for the case where both the inputs are 1, we have the carry bit as 1. So what should the K-map be? The K-map will again be a very simple one with 2 inputs on both sides, on either sides, A, B, 0, 1, 0, 1. In the K-map, we will place the one input sequence where the carry bit output is 1. That is, when A is 1 and B is also 1. So here we will place a 1. And what should be the term for this carry bit output? The term for this carry bit output should be AB. A is 1, B is 1. So the carry bit term should be AB. So the expression for C0 or C out is AB. So finally, we have 2 expressions for sum, we have the expression A XOR B, and for carry we have the expression AB. Using these two logic expressions, we can now define the internal circuitry of the half adder circuit using the knowledge of basic gates. So for that, we will first take, there are how many inputs are there? There are two inputs. One is A, the other one is B. So input A, there is a wire for input A, there is a wire for input B. Now A and B, both of them when passed to a XOR gate will result in the sum output. So this is our sum output S equal to A XOR B. Similarly, A and B both passed to an AND gate will result in the carry output. So we will take A and B and we will pass them both to a AND gate, and the output of this AND gate will be carry out equal to A and B. And this is the circuit diagram. This is called the circuit diagram. This is the final stage of working towards any combinational circuit. So at this point we have clearly identified that what is the block diagram, what is the working methodology based on which we have a truth table. Also, from using the truth table we have derived the expressions, and based on the expressions we have derived the circuit diagram. So for any combinational circuit, please remember to follow this particular sequence. First you define the block diagram. Based on the block diagram, you need to identify the working of that logic, of that circuit. What is the logic behind how that circuit works? That will give you the truth table. For what input sequence, what is the output sequence that you want to get. Based on that truth table, you need to identify the K-maps. The K-maps will give you the expressions, and these expressions will give you the circuit diagram. This is the set of steps that you need to identify for any given combinational circuit, and trust me, this does not require you to mug up anything about the circuit. This is a very logical thing. I hope you like this content. Please like and subscribe to the channel. Thank you.